You think you understand the atom in quantum mechanics. You picture it, don't you? A tiny solar system. A dense nucleus at the center, protons and neutrons packed together and electrons whirling around it in neat circular orbits. Perhaps you even remember the diagrams from school. Those little balls tracing elegant paths through empty space. It's a comforting image, familiar. It makes the invisible feel visible, makes the strange feel comprehensible. And it is, I must tell you this plainly, almost entirely wrong. Not wrong in the way that an approximation is wrong, where we simplify for convenience, but preserve the essential truth. Wrong in a deeper sense. Wrong in a way that prevents you from understanding what an atom actually is, what matter actually is, what you actually are. Most people never really ask what happens when you look closer. When you try to find that electron, to say precisely where it is and where it's going. When you demand that the atom reveal itself as a thing you can picture, they assume the strangeness they've heard about quantum mechanics, uncertainty, probability is merely technical difficulty. That if we had better instruments, sharper eyes, we would see those orbiting electrons clearly at last. This assumption is the first thing that must be abandoned. What I want to show you, what the physics of the 20th century forced us to confront, is that the atom does not resist our understanding because we lack sufficient tools. It resists our understanding because our understanding itself, the very concepts we use to make sense of the world, reaches a boundary here, a place where the familiar must not be expected to reappear in the unfamiliar. When you truly grasp what atoms are, you will not merely know more physics. You will think differently about reality, about knowledge, about the nature of the questions we are permitted to ask. Let me show you where the comfortable picture breaks down. Take that electron you imagine orbiting the nucleus. Ask a simple question. Where is it right now? Not approximately, not on average, where, precisely, at this instant. The question seems reasonable. The electron is a thing. Things have locations. We simply need to look. But when we look, and by look, I mean perform any measurement whatsoever to determine position, something peculiar happens. We find the electron somewhere. Yes, but that somewhere has no relationship to where it was before we looked. It is not that we disturbed it by measuring it, the way pressing too hard on a scale might bend its needle. It is that the electron did not have a definite position before we asked. Let me say that differently, because this is where most people's intuition rebels. The electron was not secretly located at some point, waiting to be discovered. The question, where is the electron, did not have an answer until the measurement created one. The act of observation did not reveal a pre-existing fact. It participated in bringing that fact into existence. This is not metaphor. This is not philosophical speculation dressed in scientific language. This is what every experiment, without exception, has shown for nearly a century. Consider what happens if you ask a different question. Instead of asking where the electron is, you ask, how fast is it moving? What is its momentum? You can measure this too. You can get a precise answer. But here is the terrible discovery that young Werner Heisenberg made in 1927. The more precisely you determine the electron's position, the less you can know about its momentum. The more precisely you measure its momentum, the less you can know about its position. Not because your instruments are crude, not because you made a mistake, because nature itself does not permit both quantities to exist with precision simultaneously. This is what Heisenberg called the Heisenberg uncertainty principle, and the name is unfortunately misleading. It suggests that we are uncertain, that the limitation is in our knowledge rather than in nature. But the limitation is in nature. The electron does not possess precise position and precise momentum at the same moment. These are not things it has and we fail to see. These are things that, in the quantum world, cannot coexist. Stop and think about what that means. Every object you have ever touched, every chair you've sat in, every face you've looked upon, all of it is made of atoms. And the atoms are made of particles that do not exist as discrete points moving through definite trajectories. The solid ground beneath your feet is woven from a fabric that, when examined closely, reveals itself to be something stranger than any philosophy before the 20th century had imagined possible. To understand how we arrived at this understanding and why it took the greatest minds of a generation to accept it, you must understand what came before. For 2 centuries, science had built its triumph on a simple foundation. The universe is a vast machine. Newton had shown that if you know the positions and velocities of all particles at any moment, you can calculate their positions and velocities at any future moment. The future is contained in the present, as a consequence is contained in a cause. Every event follows inevitably from what came before. This was not merely a successful method. It became for many a vision of reality itself, the universe as a clockwork, determinism as fundamental truth. Even the atoms that composed all matter were assumed to follow this pattern, tiny billiard balls bouncing according to eternal laws. Newton himself described atoms as solid, massy, hard, impenetrable, movable particles, and this picture worked magnificently for chemistry, for thermodynamics, for explaining why gases expand and why metals conduct heat. If atoms behaved like tiny balls, if they existed as definite things with definite properties, the world made sense. But there were cracks. In 1900, Max Planck discovered that he could only explain the spectrum of light emitted by hot objects if he assumed energy came in discrete packets, quanta defined by the Planck constant rather than continuous streams. He did not want this result. It contradicted everything physics had taught, but the experiments demanded it. Then came Einstein, showing that light itself behaved as particles in certain circumstances, photons, while clearly behaving as waves in others. How can something be both? The question was not yet answered. It was merely posed. Then came Rutherford, who bombarded gold foil with alpha particles and discovered that most of the atom's mass concentrated in a tiny nucleus, while most of the atom was empty space. This created the picture you carry in your mind, electrons orbiting a nucleus like planets around a sun. But there was an immediate problem. An orbiting electron, according to classical physics, should radiate energy continuously. It should spiral inward, losing energy until it collapsed into the nucleus. The whole affair should take about 100 millionth of a second. Atoms, by classical physics, should not exist, and yet they do. Niels Bohr proposed a strange solution in 1913. Electrons, he said, can only exist in certain orbits, certain fixed energy levels. They do not radiate energy while in these orbits, regardless of what classical physics predicts. They can jump between orbits, emitting or absorbing photons of specific energies, but they cannot spiral inward continuously. This violated the Pauli exclusion principle's classical expectations. No two electrons could occupy the same quantum state. This worked. It explained the spectral lines of hydrogen with extraordinary precision. But why did it work? Bohr had no explanation. He had simply declared that classical physics did not apply inside atoms, without saying what did apply instead. It took another decade, and the work of Heisenberg, Schrödinger, Born, Dirac, and others to build the mathematical framework that replaced the old certainties. Quantum mechanics, a theory that did not describe what particles are, but only what we will measure when we look for them. A theory built entirely on probability. What Heisenberg discovered in 1925 was remarkable. You could construct a mathematics of quantum mechanics using only quantities that could actually be measured, the frequencies and intensities of spectral lines. He deliberately avoided speaking of electron orbits because orbits could never be observed directly. This was matrix mechanics, and it worked perfectly. The following year, Schrödinger found a different approach, wave mechanics, that described electrons as standing waves wrapped around nuclei. This too worked perfectly. For a moment, it seemed there were two incompatible theories. Then it was proven they were mathematically equivalent, different descriptions of the same underlying reality. But what was that reality? Schrödinger hoped the waves were real waves in space, that the electron was literally smeared out. He even proposed a thought experiment, Schrödinger's cat, to show how absurd quantum superposition would be if applied to everyday objects. A cat in a sealed box could be simultaneously alive and dead until observed. Max Born showed the wave interpretation was wrong. The wave function square gave probabilities, not actual charge distributions. The electron was not spread out, the probability of finding it was spread out. I was 23 years old in 1927 when this framework came together. I am Robert Oppenheimer, and I had just arrived in Göttingen, where Heisenberg and Born were working. The atmosphere was, I can only call it, electric. We knew we were present at a revolution, not merely a new theory, but a new conception of what theories could be. Let me now explain what quantum mechanics actually says about the atom, not the simplified version, the real thing. First, abandon the image of the electron as a particle traveling through space. What quantum mechanics gives us instead is something called a wavefunction. This is a mathematical object represented by the Greek letter psi that describes all the information that can be known about the electron's state. The wavefunction does not tell you where the electron is. It tells you the probability of finding the electron at each possible location if you perform a measurement. Before measurement, the electron does not exist at any particular place. It exists as a spread of possibilities, a cloud of potential locations, each with its own probability. This is not a cloud of uncertainty in our minds. This is a cloud of genuine indefiniteness in nature. The wave function for an electron in a hydrogen atom, for instance, forms shapes that chemists call orbitals. The electron is not orbiting the nucleus. That word implies a trajectory, a path through space. The electron is spread through a region, more likely to be found in some places than others, but without being definitely located anywhere until observed. I contributed to understanding how this works for molecules. Max Born and I showed in 1927 that because atomic nuclei are nearly 2,000 times heavier than electrons, they move vastly slower. This allows us to treat the nuclei as approximately stationary while solving for the electron's wave functions. The Born-Oppenheimer approximation, it came to be called. This mathematical trick is why chemistry works, why we can draw molecular structures with atoms in fixed positions. But I want to be clear, this is an approximation. The nuclei, too, are quantum objects. Their positions, too, are probability distributions. We simply pretend otherwise because it makes the calculations possible. Here is where it gets stranger. The wave function is not merely a statistical summary of where the electron might be found. Until measurement, the electron is, in some genuine sense, in all those places simultaneously. Not potentially, not metaphorically. The mathematics describes a superposition of states. The electron exists as a combination of being here and being there and being everywhere it could be. This superposition is not merely a statement about our ignorance. We can test it. If electrons were secretly in one location and we simply didn't know which, certain experiments would come out one way. If electrons are genuinely in superpositions of locations, those same experiments come out differently. The experiments agree with superposition. The electron is, I lack better words, genuinely smeared across space until observation collapses this smear into a single result. Think about what that means for your body. You are composed of approximately 7 octillion atoms. That number is 7 followed by 27 zeros. Every one of those atoms consists of a nucleus surrounded by a probability cloud of electrons. The apparent solidity of your hand, the definite boundary of your skin, these emerge from the collective behavior of quadrillions of indefinite entities. How does solidity emerge from uncertainty? This is where the quantum world touches your everyday experience. The electrons in atoms repel each other through electromagnetic force. Their probability clouds cannot overlap too closely without enormous energy costs. When you press your hand against a table, the electrons in your hand's atoms do not touch the electrons in the table's atoms. They never touch anything in the classical sense. Their wave functions repel each other. What you feel as resistance, as solidity, is electrons that exist as probability distributions refusing to let those distributions overlap. The apparent hardness of matter is a quantum effect. The apparent impenetrability of objects is a quantum effect. When you walk across a floor without falling through, it is because the quantum mechanical pressure of electrons in the floor's atoms resists the quantum mechanical pressure of electrons in your feet. You have never touched anything in your life. Not really. Not the way Newton would have meant it. This should completely restructure how you see the physical world. There is another aspect of quantum mechanics that I want you to understand, because it touches on a question that has occupied human thought for millennia. What is the relationship between the observer and the observed? It interferes with itself. It passes through both slits simultaneously as a wave function spread across space, and the probabilities interfere with each other. Here is where the mystery deepens. If you place a detector at the slits to determine which slit each electron passes through, the interference pattern vanishes. The electrons now behave like particles, making two bands. The very act of asking which slit changes the answer to the question, where will it land? This is not because your detector disturbed the electron physically. You can design detectors that interact so weakly that no classical disturbance could explain the effect. The interference disappears because you obtained information about the path. The nature of your question, the type of measurement you chose to make, determines the type of reality that emerges. Think carefully about what this implies. The electron does not have a definite path through the apparatus until you ask about it. The property, which slit did it pass through, does not exist until you measure it. And measuring that property precludes measuring other properties, the wave-like interference that would have existed if you hadn't asked. This is not a limitation of our knowledge. This is the structure of reality. I must now address the deepest puzzle, the one that troubled Einstein until his death, and which I believe he never fully accepted. When you measure an electron's position, you get a definite answer. Before measurement, the wave function described probabilities spread across space. After measurement, the electron is definitely here, not there. What happened to all those other possibilities? The standard view associated with Niels Bohr and what came to be called the Copenhagen interpretation is that measurement causes the wave function to collapse. The spread of probabilities suddenly reduces to a single actuality. The electron was everywhere. Now it is here. This quantum decoherence explains how classical reality emerges from quantum possibilities. But this raises an obvious question. What counts as a measurement? What is special about the act of observation that causes this collapse? Bohr's answer, which I found profound, though others found evasive, was that quantum mechanics does not describe the microscopic world in isolation. It describes the relationship between the microscopic world and the macroscopic apparatus we use to probe it. There is no clean separation between observer and observed. The measurement apparatus, the questions we ask, the experiments we design, these are part of the physics. This is Bohr's complementarity. The electron is not a particle. The electron is not a wave. It manifests particle-like properties in some experiments and wave-like properties in others. Both descriptions are needed. Neither is complete alone. They complement each other, like the two sides of a coin that cannot be seen simultaneously. Einstein never accepted this. He believed, he felt it in his bones, that the electron must have definite properties whether we measure them or not. That quantum mechanics, however successful its predictions, must be incomplete. That some deeper theory awaited discovery, one that would restore the determinism that Newton had established. Later, Bell's theorem would prove Einstein wrong about quantum entanglement, showing that no hidden variables could explain quantum correlations. I understood his discomfort. The quantum world offends our deepest intuitions, but the experiments have spoken, repeatedly and unambiguously. No hidden variables have been found. No deeper determinism has emerged. The probabilistic nature of quantum mechanics appears to be fundamental. Let me tell you what this means, in language borrowed from an older tradition. In Hindu and Buddhist philosophy, there is an understanding that our concepts have limits, that the categories we use to divide and organize experience do not necessarily correspond to the structure of ultimate reality, that the world, at its deepest level, may resist the frameworks we impose upon it. I studied Sanskrit for many years. I read the Bhagavad Gita in the original, and I came to see that the paradoxes of quantum physics are not wholly unfamiliar, not wholly unheard of, not new. What we found in atomic physics are illustrations, examples, encouragements, refinements of old wisdom. Consider the Buddhist teaching about the self. Is the self the same from moment to moment, or different? Is it permanent or changing? The Buddha's answers to such questions were famously elusive, because the questions themselves presumed categories that did not apply. Compare this to asking about the electron. Does it have a definite position? The answer is not yes or no. The question presumes a classical framework that does not apply. Is the electron at rest? No. Is it in motion? Also no. These are answers, as I once wrote, not familiar for the tradition of 17th and 18th century science, but they are not wholly unfamiliar for certain other traditions of human thought. There is more to say about what quantum mechanics reveals, and I want to be precise about the implications. First, consider the nucleus itself, the tiny core at the atom's center that I have spoken of as if it were a stable foundation. It is not. The nucleus is a seething cauldron of particles held together against their natural repulsion by forces that were not understood until my generation discovered them. Protons, which carry positive electric charge, should repel each other violently at the short distances found within a nucleus. They do not fly apart because another force binds them, the strong nuclear force, which operates only at extremely short range and which overwhelms electromagnetic repulsion within that range. But this binding is not perfect. It is not eternal. In many nuclei, the configuration is unstable. Given enough time, the nucleus will transform emitting particles, releasing energy, transmuting into a different element entirely. This is radioactivity. The decay of uranium, the radiation of radium, the half-lives of isotopes, all consequences of the quantum nature of nuclear forces. The energy stored in atomic nuclei is vast beyond ordinary comprehension. When Einstein wrote his famous equation relating mass and energy, He revealed that a small amount of mass corresponds to an enormous amount of energy. The strong nuclear force, binding protons and neutrons together, stores energy in the bonds themselves. When heavy nuclei split fission or light nuclei combine fusion, that binding energy can be released. A single gram of matter, if fully converted to energy, would release as much as 20,000 tons of high explosive. This is not metaphor. This is measured fact. But in ordinary atoms, this energy is locked away. The quantum mechanical barriers that prevent nuclei from spontaneously rearranging are enormous. The energy is there, but inaccessible like water behind a dam too thick to breach. Except that quantum mechanics also provides a way through barriers that classical physics would deem impenetrable. This is called quantum tunneling. A particle approaching a barrier it lacks the energy to climb can nevertheless appear on the other side because its wave function extends through the barrier and has some probability amplitude beyond it. Every radioactive decay involves this tunneling. The alpha particle inside a uranium nucleus does not have enough energy to escape classically, but its wave function leaks through the nuclear barrier, and occasionally, purely by chance, the particle manifests outside. When it does, the nucleus has transformed. This is why radioactive half-lives exist. This is why we can predict that half a sample of radioactive material will decay in a characteristic time, even though we cannot predict which atoms will be the ones to decay. And here, quantum mechanics reveals something even more unsettling. Radioactive decay is genuinely random, not random because we lack information, random in principle. If you have a collection of radioactive atoms, you can predict with great precision what fraction will decay in the next hour. But you cannot predict which specific atoms will decay. There is nothing different about the atoms that decay versus the atoms that don't. Nothing hidden, nothing that determines which is which. Einstein found this intolerable. He famously said that God does not play dice with the universe. Bohr's response was equally famous. Stop telling God what to do. I sided with Bohr, not because I was certain, but because the evidence demanded it. The experiments showed genuine randomness at the quantum level, not apparent randomness masking deeper patterns. Genuine, fundamental, irreducible chance. This means that certain questions have no answers, not because we haven't discovered the answers yet, but because the universe does not contain them. The universe is, at its foundations, less determined than Newton imagined. This realization carries weight beyond physics. For centuries, philosophers debated whether human beings have free will, or whether our actions are determined by prior causes, our brains following the same mechanical laws as billiard balls. Quantum mechanics does not settle this ancient debate, but it does remove one argument entirely. The universe is not a deterministic machine. At its deepest level, nature permits genuine novelty, genuine alternatives, events that are not fully specified by all that came before. I do not claim this proves free will exists. The connection between quantum randomness in atoms and human choice is not straightforward. But I do claim this. The picture of the universe as a vast clockwork, ticking forward through predetermined states from beginning to end, is simply wrong. That picture must be abandoned. What replaces it is stranger and, I believe, more honest about the complexity of existence. Let me now make this concrete. Let me show you how quantum mechanics touches the visible world. When you see color, you are detecting photons, particles of light emitted by electrons jumping between energy levels in atoms. Each element produces specific colors because each element has specific allowed energy levels, and the photons emitted when electrons jump between them carry specific energies. This is why neon glows red, why sodium lamps glow yellow, why every element has its own spectral fingerprint. Quantum mechanics explains all of this, explains it precisely, explains it completely. When you warm yourself by a fire, you receive energy that was released by electrons in carbon atoms, forming new bonds with oxygen atoms. The energy differences between those quantum states becomes heat that reaches your skin. Every fire you have ever built was a quantum mechanical process. When you see your reflection in a mirror, it is because photons striking the metal's electrons are re-emitted rather than absorbed. The electrons exist in quantum states that cannot absorb visible light without more energy than the photons carry. So the photons bounce back. You see yourself because of quantum mechanics. The transistors in your computers, the lasers in your devices, the GPS satellites calculating your position. Every one of these technologies depends on quantum mechanics being exactly right, not approximately right, not metaphorically right, precisely correct in its predictions, down to as many decimal places as we can measure. The laser works because electrons in certain materials can be stimulated to emit light in perfect lockstep photons with identical wavelength and phase marching together in a beam. This is only possible because quantum mechanics permits certain states and forbids others. The transistor works because electrons in semiconductors can be manipulated to flow or not flow based on quantum mechanical properties of the material's energy bands. These are not classical devices improved by quantum corrections. They are fundamentally quantum devices that could not exist in a classical universe. Every moment of your digital life depends on the strange probabilistic world I have described being precisely, exactly true. And the future promises even more direct applications. Quantum computing harnesses superposition and quantum entanglement to process information in ways that would be impossible classically. Where classical computers process bits that are either 0 or 1, quantum computers use quantum bits, qubits, that exist in superposition of both states simultaneously. This quantum parallelism could solve certain problems exponentially faster than any classical computer. And yet, despite this extraordinary success, we cannot visualize what is happening. We cannot form mental pictures of the quantum world that satisfy our intuition. Every image we create is a metaphor, a simplification, a translation from mathematics into a language that is fundamentally inadequate. Some find this troubling. I find it liberating. We have discovered that our concepts developed over millennia of dealing with medium-sized objects moving at moderate speeds are provincial. They work in their domain magnificently, but they are not universal. The atom exists beyond that domain, and in studying it, we have had to expand our sense of what understanding itself can mean. I want to close with something larger than physics, something about what this knowledge does to us and for us. We often speak of science as a search for truth, and so it is. But the truth we find is not always the truth we expected. Sometimes it reveals the limitations of the very framework we used to search. Quantum mechanics forces us to recognize that the fact that we were in the habit of talking a certain language and using certain concepts did not necessarily imply that there was anything in the real world to correspond to these. Our progress is narrow. It takes a vast world unchallenged and for granted. This is one reason why science, for all its revolutions, is conservative. And yet, within that narrow progress, we have found something extraordinary. We have found that nature, at its deepest level, is more subtle than common sense allows. That the solid, massy, hard, impenetrable particles Newton imagined are not what we find when we look closely. That reality is full of gaps and cracks, more of a void than a substance. This does not diminish us. It enlarges us. The atoms of your body were forged in stars that exploded billions of years ago. Those atoms carry within them the quantum strangeness I have described, the probabilities, the superpositions, the collapse of wave functions, the complementarity of particle and wave. You are not merely matter. You are quantum matter. Your existence depends on principles that no philosophy before the 20th century could have imagined. I once said that science is an open house, open to all comers. The rooms are not arranged in a line or a square or a circle, but with a wonderful randomness suggestive of unending growth and improvisation. There are no locks. There are no shut doors. Wherever we go, there are signs and usually the words of welcome. But scientists live elsewhere also. Live in houses where the rooms are not labeled atomic theory or genetics or the internal constitution of stars, but quite different names: power and production and evil and beauty and history and children and the Word of God. The atom is not merely a subject for specialists. It is the foundation of the world you inhabit. And understanding it, truly understanding it, with its strangeness intact rather than papered over, changes how you see that world. That is what the atom really is. Not a tiny solar system, not a billiard ball, not something that yields to common sense when examined closely. The atom is a demonstration that reality is deeper than intuition, stranger than expectation, and far more beautiful than any simple picture could convey. It is an opening up of the human spirit, avoiding its provincialism and narrowness. When Bertrand Russell once lectured on quantum mechanics at Harvard, Professor Whitehead, who presided, thanked him afterward, and not least, he said, for leaving the vast darkness of the subject unobscured. I have tried to do the same, to explain without falsely simplifying, to illuminate without pretending the darkness isn't there. Because the darkness itself is part of the truth. The strangeness of the quantum world is not an obstacle to understanding, it is the understanding. To know the atom is to know how much remains to be known. And in that knowledge, Properly grasped, there is wonder enough for any lifetime